Some solved problems for chapter 17. So here we have an electron. We're going to stick it in a potential difference, and what's going to happen is it's going to obviously run away from these positive charges and accelerate. And this potential difference is going to do some work on this electron. The amount of work that it's done is going to be equal to the negative charge multiplied by the potential. And the work that this field does is going to be the kinetic energy gained by the electron. So the kinetic energy is going to be equal to the work done. So negative charge multiplied by the voltage. So negative, the charge is an electron, so negative 1.6 times 10 to the negative 19th multiplied by the potential difference of 18,500. So the kinetic energy is going to work out to be 2.96 times 10 to the negative 15 joules. So that's the answer to part A. In electron volts, we just need to convert joules to electron volts, so 2.96 times 10 to the negative 15th joules. And I know that 10 to the negative 19th joules is 1 electron volt, so go ahead and you type all that in, and we're going to get 1.85 times 10 to the 4th electron volts, which is also simply the voltage. And for problem number 19, we have some point charge creating some potential that we know, and we know how far away we are from that charge, and we're simply looking for what that charge is. Well, we know that V is going to be equal to KQ divided by R, that lowercase. And so Q is simply going to be the potential multiplied by the distance divided by K. So 165 volts multiplied by 0.15. Divide that guy by 9 times 10 to the 9th. And I'm going to come up with my charge being 2.8 times 10 to the negative 9th coulombs. Okay, a little bit more practice with potential. Here we have kind of a charge distribution, so charge 1, charge 2, and charge 3. And I'm looking for the potential right there. Well, we could write the potential from any one of these charges as KQ divided by R. And essentially all I'm going to do is I'm going to say the potential at A is simply going to be the potential from 1 plus the potential from 2 plus the potential from 3. One thing about potential versus electric field is I don't have to worry about any directions at all because potential is very simply a scalar. So this is going to be K multiplied by a plus 3Q divided by the distance L plus K multiplied by a positive Q divided by the distance. Figure this distance out, draw a triangle, Pythagorean theorem. Distance is going to be equal to the square root of L squared plus L squared, and it's going to come out to be the square root of 2 multiplied by L. So square root of 2 multiplied by L plus K. Now I've got my negative 2Q. Divide that guy by L. And now we can kind of simplify this a little bit. We can add this one and this one. They do have a common denominator. This one's a negative 2Q, this one's a plus 1, so it's going to be KQ divided by L plus KQ square root of 2 multiplied by length. And if you really wanted to impress me and be fancy, you would write this as KQ divided by L, factor all those out, and 1 plus 1 over the square root of 2. You could probably even type that into your calculator if you want, but this is fine. Okay, a problem with a capacitor. Essentially, draw some plate. You're going to draw some positive charge right there. Got some charge separation. We have a capacitor. So we know what this charge is, and we know what the voltage is, and we're looking for the capacitance. Well, we have one equation to deal with for capacitors, and charge and voltage. Q is equal to CV. So C must be equal to Q divided by V. So 2.5 times 10 to the negative 3rd, divide that guy by 960. We're going to come up with 2.6 times 10 to the negative 6 farads, or 2.6 microfarads. Okay, here we have a capacitor, and we're given some information such as the electric field, the area, the distance of separation, and what we're looking for is the charge on each plate. One thing to kind of be careful of is the units. Essentially, we always want to work in meters. And I've gone ahead and I've converted this distance into meters. This is in square centimeters. I need it in square meters. So I need to do a little bit of unit conversion. 1 meter, 100 centimeters. But I'm not quite done yet. This is centimeters squared. I need to go ahead and square this guy such that this will now cancel out with that because of the squaring. And so I'm going to have to work. So this is going to be my expression for area. Now I'm looking for the charge. I only have one expression for the charge, capacitance multiplied by voltage. But I also do know that capacitance can be written as permeability of free space, area divided by the distance. So let's go ahead and put that guy in. I know the area and I know the distance, and I got my voltage, but I don't know my voltage. I do, however, know the electric field. The electric field can be written as the voltage divided by the distance. So I can say this is the permeability of free space, area, multiplied by my electric field, where I've simply replaced this guy with that guy. Now I know all these things, so I can go ahead and plug all these in. 10 to the negative 12th. Got my area, 45 times 10 to the minus 4. Again, be careful there. And the electric field, 8.5 times 10 to the 5th volts per meter. And I'm going to end up with a capacitance of 3.39 times 10 to the negative 8th, or end up with a charge of 3.39 times 10 to the negative 8th coulombs. And the last problem, I'm looking at energy storage inside of a capacitor. Got some information about the capacitor, the length, the width of the sides, distance of separation, and the charge on each one. And essentially we know that the potential energy of a capacitor is going to be 1/2 charge squared divided by the capacitance. Well, I know what the charge is, I just need the capacitance. So capacitance is going to be equal to permeability of free space, the area divided by the distance of separation. So 8.85 times 10 to the negative 12th multiplied by my area. That's just going to be the length multiplied by the width, so 0.08. 0.08. Distance of separation, 1.5 times 10 to the negative 3. Again, had to convert that to meters. And I end up with a very tiny capacitance of 3.77 times 10 to the negative 11 farads. And so now my potential energy is simply going to be 1/2. Got my charge squared, so 370 times 10 to the negative 6. Make sure I square that guy. Divide by my capacitance, 3.77 times 10 to the negative 11th. And wind up with about 2,000 joules.